Welcome everyone to today's session. We are here to discuss the core philosophy of being a pragmatic Go developer. As the title suggests, Go is built on the idea of being batteries included, but not bloated. This means the language provides a robust and comprehensive standard library that gives you the tools you need to build production-ready applications without the extra weight of unnecessary dependencies. Today, we will explore how to leverage this balance of power and simplicity to write cleaner, more efficient code. Let's get started. Building without the bloat is a core philosophy of the Go programming language. As illustrated by this comparison, many development environments rely on a chaotic accumulation of third-party dependencies and heavy frameworks. Go takes a different approach. Its standard library is meticulously engineered to provide exactly what is necessary to build production-ready network services, command line tools, and complex concurrent systems. By utilizing this robust and comprehensive built-in toolkit, developers can achieve high-performance production readiness without the burden of a sprawling and often fragile external ecosystem. Foundational abstractions represent the core pillars of the Go standard library, providing the essential building blocks for robust application development. Beginning with web and network, the net/HTTP package enables the creation of highly concurrent servers with minimal boilerplate. This is complemented by encoding/JSON for native data marshalling and net/HTTP/HTTP test, which facilitates the rapid deployment of local servers for isolated testing. Shifting to concurrency and flow, we have the context package, which acts as a universal glue for managing state and the propagation of cancellation signals across distributed systems. When more granular control is required, the sync package offers low-level locking mechanisms to ensure thread safety. Lastly, our I/O and utilities category highlights the elegance of the I/O package. By utilizing the I/O.reader and I/O.writer interfaces, Go achieves efficient, tiny footprint streaming that scales seamlessly. Rounding out this section are database/SQL for standardized database connectivity and the comprehensive time package for precise temporal operations. The pragmatic workflow represents an end-to-end development lifecycle, powered entirely by the core Go toolchain. This approach eliminates the need for third-party APM agents or external testing frameworks, keeping your environment clean and your dependencies minimal. The process begins with the build phase, where we leverage the standard net.http and context packages to construct robust, production-ready services. Once the foundations are in place, we transition to the verify stage. Here, the built-in testing and HTTP test packages provide all the necessary tools to validate our logic and ensure reliable API behavior. After verification, we move to measure. By utilizing Go test with the benchmark flag, we can accurately quantify performance and identify areas for potential improvement. This leads directly into the final stage, optimize. With the native pprof tool, we can perform deep dive profiling to refine our code, reduce resource consumption, and maximize efficiency. By following this four-step lifecycle, you can develop, test, and tune high-performance Go applications using nothing but the language's native capabilities. Phase 1 of the build focuses on zero-dependency routing. By using Go's standard library, we can initialize a multiplexer with http.newServMux, map specific endpoints like /process to handler functions, and launch the server on port 8080. This method effectively replaces the need for heavy web frameworks such as Spring or Express. The standard library multiplexer is remarkably capable, and with the significant routing enhancements introduced in Go 1.22, it provides all the functionality required for modern web services without adding external dependencies. During the initial build phase, we prioritize efficiency and concurrency within the API handler through two primary mechanisms. First, we utilize streaming JSON by passing the request body directly into the decoder. This method avoids the memory overhead associated with reading large payloads into strings, allowing for more scalable data processing. Second, we implement context cancellation using the select pattern. If a client drops their connection, the net/HTTP package triggers the context's done channel, enabling the handler to instantly abort downstream database queries. This proactive resource management ensures that server capacity is preserved for active requests. In Phase 2, we explore the testing paradigm. Go's standard library significantly lowers the barrier to entry for testing, often making it faster to write an automated test than to perform manual verification via curl or Postman. The built-in toolkit natively supports unit tests, parallel test execution, and table-driven patterns, along with integrated fuzzing capabilities. This comprehensive suite eliminates the need for external frameworks like Jest or JUnit, ensuring a streamlined and consistent testing experience across the entire Go ecosystem. The net/http/http test package serves as a powerful tool in your Go testing arsenal. It enables the simulation of an entire HTTP lifecycle, including request generation, routing, and response capture, all without the need to open an actual network port. This effectively eliminates common CI/CD issues, such as address already in use errors. As illustrated in the diagram, the process begins with a mock request. This request has passed directly into your API handler, mimicking the behavior of a live environment. The critical component here is the HTTP test.response recorder. Because this recorder implements the standard HTTP.response-writer interface, your production code remains entirely unaware that it is being tested. It writes the response to the recorder exactly as it would to a real network connection. This allows you to precisely inspect the resulting status codes, headers, and body, ensuring your handlers behave correctly while keeping your test suite fast, isolated, and reliable. Let's examine the anatomy of a pragmatic test, focusing on how to efficiently test HTTP handlers. This approach follows 4 distinct steps to ensure reliability and speed. First, we prepare the data. We take our payload and marshal it into a JSON byte slice, which serves as the content for our request. Second, we create a dummy request. Using the standard library's newRequest function, we specify the post method and the target endpoint, then wrap our byte slice in a buffer. This simulates a real incoming request without the need for an active network connection. Third, we initialize the SPY. By calling http-test.newRecorder, we create a mock response writer. This object records everything the handler does, such as writing headers or body content, so we can verify the results afterward. Fourth, we invoke the handler directly. We pass the recorder and the dummy request into the handler's serve_HTTP method. By bypassing the network stack entirely, this pattern eliminates flakiness and ensures that our test suite executes in mere milliseconds, providing immediate feedback during development. Phase 3 focuses on catching performance regressions. While functional correctness is essential, ensuring code works is only half the story. We must also quantify its cost in terms of CPU and memory usage. Go provides robust, built-in benchmarking tools that simplify this analysis. By running the command go-test-bench-dot-benchmem, we can generate detailed reports on execution time and memory allocations. In the implementation, we use b.resetTimer to exclude initialization overhead from our results, then execute the target logic within a loop that runs b.endTimes. This leverage of high-precision timing and memory statistics built directly into the testing.b package allows us to detect efficiency regressions early in the development cycle. Understanding benchmark metrics is essential for accurately diagnosing and improving application performance. Looking at a standard benchmark output, we can break it down into 4 critical components. First, the number 200,000 represents the loop iterations. This high count ensures that our results are statistically significant by smoothing out transient system fluctuations. Second, we have the execution speed, measured here at 6,500 nanoseconds per operation, which equates to approximately 6.5 microseconds for each individual request. Third, we observe the memory footprint of 448 bytes per operation, indicating the amount of memory allocated on the heap during every cycle. Finally, the allocation count tells us there are 9 distinct memory allocations per operation. Pragmatism in performance tuning often centers on reducing these allocations. If this count jumps significantly, for example from 9 to 90, it is a clear indicator that a performance bottleneck has been introduced, which will likely increase garbage collection pressure and decrease overall throughput. Phase 4 introduces the pprof X-ray machine, a powerful tool that allows you to move past guesswork. pprof provides a literal map of CPU cycles and memory heap allocations, visualized as a directed acyclic graph. Implementation is remarkably simple. As seen in the code snippet, a single blank import of the net.http/pprof package is all it takes. This action automatically registers profiling endpoints under the /debug/pprof path on your default server, giving you immediate and deep visibility into your application's performance characteristics. To effectively identify performance issues, we can use the Go pprof tool to generate a flame graph, which visualizes CPU bottlenecks in a clear and intuitive way. In this chart, the horizontal width of each bar represents the percentage of total CPU time spent within that specific function and its children. The vertical axis represents stacking, which shows the call depth of the execution path. By analyzing the width, we can immediately spot where the most time is being consumed. For instance, the very wide bar for JSON.unmarshal shown here reveals that JSON parsing is the actual bottleneck in this process, rather than the database. This allows developers to focus their optimization efforts on the specific code paths that will yield the greatest performance improvements. To effectively pinpoint memory leaks, it is essential to identify which specific lines of code are allocating objects on the heap rather than the stack. By utilizing the Go tool pprof with the alloc_objects flag, as shown in the command here, we can generate a profile and view it in an interactive web interface. This approach exposes the exact source of a high number of allocations per operation, allowing us to scrutinize the source code and identify the precise location where optimizations are needed to reduce memory pressure. The pragmatic beauty of Go's standard library is rooted in its strict adherence to stability. As this timeline illustrates, code written using these packages a decade ago still compiles and runs efficiently today. This level of backward compatibility is a core strength of the Go ecosystem, ensuring that legacy applications remain functional and performant on modern infrastructure without requiring extensive maintenance or refactoring. By prioritizing stability, Go provides a reliable foundation that allows developers to invest in long-term projects with confidence.